Hi. In this last presentation of the regular sequential circuits playlist, we will look at the case of binary counters. After watching this presentation, I hope that you will be able to write VHDL descriptions for universal binary counters and also for modulus n counters. These types of circuits are actually very common, and we will use them frequently throughout our course. What you are looking at here is a bidirectional counter that can be preloaded to any given value, and that can also be cleared synchronously. You may pause the video at this point if you want to have a more detailed look at this VHDL description, but before you do so, let me call your attention to two main aspects. The first one is the difference between the asynchronous reset and the synchronous clear signals. The asynchronous reset is just the usual construct that we have already used several times before. If the reset input is brought to 1, then the counter output will be set to 0. Now, if you look at the process description, you will see that it can be activated by either the clock or reset inputs. So if reset goes high, then the process will be activated and the counter outputs will be set to 0 immediately. And this will happen even if there was no rising edge transition on the system clock. And that is why the reset input is asynchronous. Now, on the other hand, if the synchronous clear input goes high, then the register underscore next signals will go immediately to 0, as indicated here in the next state logic, which belongs to the combinational logic segment in this description. This will happen immediately. However, the register outputs, they will be set to 0 only whenever there is a rising edge in the system clock. So the next state value will be taken to 0 as soon as the synchronous clear goes to 1, but the counter outputs, they will be set to 0 only at the next rising edge of the system clock, which is when the process is activated and the register outputs are updated. Now, the second aspect deserving your attention is the need to perform a type conversion operation. And this comes from the fact that arithmetic operations are not supported in the standard logic vector data types, which was the data type defined in the entity description for the counter inputs and outputs. So the signals R underscore next and R underscore register were defined in the architecture block as the as unsigned for this reason, and therefore we will need to convert from standard logic vector into unsigned before incrementing or decrementing. And likewise, we will have to convert back from unsigned into standard logic vector to update the counter outputs. Finally, let me call your attention to the fact that we are generating two combinational outputs to indicate when the counter reaches the maximum and minimum values. The modulus n counter presented in this slide doesn't support any other control inputs besides the usual asynchronous reset signal, which is declared and used in the usual form. The thing to notice in particular here is the way to force the counter reinitialization when the limit value n is reached. But the corresponding statement is very much self-explanatory, as you can see here. So the next value will be defined as 0 whenever the current counter outputs reach the limit that was defined for the modulus counter. As you may see by checking the full VHDL description for this block, which is presented in pages 82 and 83 of the book, the limit m was defined as a generic declaration in the entity description. Now, like in previous cases, I very much recommend you to open the corresponding VHDL files that are available in our course website and to use them in the Xilinx design environment to simulate the operation of the various blocks and also to observe what happens when you make changes. Thank you for your attention.